Okay. Thank you for giving me this opportunity, and it's good to see you all. And at least I know a few of you. And good to see you, Obi. Uh, and just to start my presentation, climate and land use change impacts on stormwater generation in South Florida. This presentation is based on a recent paper that I published with my student. I'm currently an associate professor in the Department of Civil and Environmental Engineering at West Virginia University in Morgantown. I started this work when I was in Florida International University as an assistant professor of civil and environmental engineering. So, and this is my lab. And I'm sorry, part of the slide is, it looks like it's not showing up, but I'll do the best I can with the present one. Okay, next slide, please. Okay, here is the background, and I think this is kind of redundant after the previous presentations. So, with increasing with increasing warming, changing climate, we are expected to see increased rainfall intensity and frequency, and Florida is still growing in terms of urbanization. So, imperviousness cover is expected to increase. Basically, pavement is increasing, and you have then elevated groundwater level due to sea level rise. So, as Dr. Obisekara mentioned. So, in a coastal environment like South Florida, this does is basically it creates high risk of pluvial flooding, and as well as fluvial flooding. By pluvial flooding, I'm referring to the stormwater flooding that's mainly caused by the rainfall accumulation on the ground due to insufficient drainage. Next slide, please. So what we did here is we used US EPA stormwater management model, and we developed a large-scale model and with fine spatial resolutions. Basically, we split this 7,000 square kilometer urban, mainly urban area. Yes, and you can see that there are natural areas as well. So it covers from Florida City at the south through the Fort Pierce, so in the north. So, and it has mainly urban land uses, as you can see by the red colors, and then you have also emergent wetland and deciduous forest. So, you know, I'm not going to go much into the detail into the model. So you can see from this simple schematic that there are many rainfall stations, like 71, and we split the basin into 333 sub-basins, and we inputted data from 410 groundwater stations, and we have parameterized, basically we represented the canals and streams in this area with 431 segments, river segments, and 433 nodes. Next slide, please. Okay, here is a, excuse me, here is a calibration and validation plot. We calibrated the model with stream flow data, and for approximately 10 years of calibration and 5 years of calibration and 5 years of validation from 2006 to 2013. So at 6 different outlets, major rivers such as Miami River, and then, you know, Hillsborough Canal and things like that. Next slide, please. Okay, I'm going straight into the results. So as Dr. Obisekara showed that, you know, temperature is clearly increasing. Rainfall has some mixed pattern. So we use 20 global climate model projections of CMIP5, and we have ensembled those. So you will see that by 2050s, RCP 4.5, which is supposed to be a less aggressive scenario, than RCP 8.5, you can see that under only changing climate, basically under only changing rainfall, which is expected to increase up to 30% in this area, and based on the ensemble GCM average, basically. So what we see that under climatic changes, basically rainfall increases, spatial mean rainfall increases, ranges from 142 to 267 millimeter under different scenarios. But under RCP 4.5, you see that by 2050s, you have most of the increases happening. And then by 2080s, RCP 4.5, a little bit more increase, perhaps, based on this map. And but 8.5, you are having less increase. And by 2080s, RCP 8.5 is even lower increase of runoff under increasing rainfall. The reason is, as we go beyond 2050s, the model uncertainty increases. Some models are predicting decreases in rainfall. So when we ensemble, in the average, it decreases in the longer range, means in the next 50 years. But in the next 30 years, it's more into consensus that more models are predicting increases in rainfall. Spatial mean rainfall increases range from 174 to 407 millimeter. In response, spatial mean runoff increases range from 142 to 267 millimeter. Higher spatial mean runoff increases of 241 to 437 millimeter were noted at and around urban centers in the basin. I'm talking about the red areas, mainly in the city of Miami, greater Miami area, greater Fort Lauderdale, and keep moving north is the north central, if you will say that, area that will experience the most runoff increases under changing climate, in other words, under increasing rainfall and increasing ET. Next slide, please. Now, what about land cover? And you see that under increasing land cover, runoff increases range from 70 to 98 millimeter, which is much less than the increase due to increasing rainfall. And that's understandable because most of the area here is already urbanized. So you're not going to increase the imperviousness at the same rate as the rainfall is going to increase. So as you can see that 7 to 10 percentage point increase in imperviousness are predicted by EPA data set. So, but still, if we see that where you have the most runoff increases, higher runoff increases were noted at and around urban centers, once again in the basin. The reason is, people don't go in the middle of the pasture or herbaceous wetland to build. They basically expand the urban area. So that's why you see that at and around urban centers, due to increasing land cover, increasing imperviousness of pavement, you're getting most runoff increases. So next slide, please. How about we run the model together, like increasing rainfall, ET, and increasing imperviousness in land cover. And you can see that clearly the area around the urban centers became even more red. So basically what is saying that under concurrent climatic and land cover increase changes, spatial mean runoff increases range from 244 to 367 millimeter. Urban centers from the north central to the south central region, including Fort Lauderdale, Boca Raton, Fort Lauderdale, and then city of Miami and greater Miami, I should say. They would experience higher spatial mean runoff increases of 323 to 499. Once again, most of the increases are happening by 2050s and under 4.5 scenario, and by 2080s under RCP 8.5 scenario, we have more Uncertainties in the rainfall projections, increases and decreases mixed. Therefore, you are going to get less increase in mean runoff. So the greater Miami area, from this map, we can see that the greater Miami area would experience the highest increases in runoff under all 4 scenarios. Next slide, please. So the relative, if you look at this figure, the relative basin runoff increases in the 2050s and 2080s under concurrent climatic and land cover changes are higher than the superimposed runoff increases under standalone changes in climate and land cover. That shows synergistic increases. That means we cannot just treat this runoff increases standalone under changing climate, means increasing rainfall or increasing ET, or under land cover. We cannot do management that way because we are going to fall short in our projections. So there is some non-linear increases. So therefore, we have to plan based on concurrent climate and land cover increases, and you see that it can increase up to 110%, even by 2080s, RCP 4.5. This is the longer term scenario, 50 years, excuse me. And by 2050s, RCP 4.5, you can see that an increase of around 100%. That means stormwater is expected to increase even in the next 30 years in an average sense in the basin, like by double. Okay, so it's not going to be the same in all over the area, but this is an average estimate over the whole basin. So what would be the most critical future runoff scenario for infrastructure design, construction, and maintenance in South Florida? In the near term, it's 2050s RCP 4.5. In the longer term, means 50 years, we are saying 2080s RCP 4.5. Next slide, please. So overall, stormwater runoff could double, as I said, by 2050s to 2080s. And we have seen that climate predominantly drives increases in stormwater runoff in urban areas more than the land use changes. Now, we have some talk today about sea level rise. We are interested to see how sea level rise is going to increase the stormwater runoff generation in the watershed. So interestingly, we expected that there will be significant increase, but interestingly, we have seen that this is a minor contributor in increases in stormwater runoff per se. But there are areas which are very close to the coast. There we have seen some notable increases. Otherwise, away from the coast, groundwater sea level rise, increasing groundwater level did not significantly impact or increase the runoff generation. That was kind of a counterintuitive results for us, but I think I understand why, because this kind of hydrologic model, they take care of the groundwater surface water exchange through the elevated canal water level. It does not necessarily increase the groundwater level due to the sea level rise. It's not designed that way. However, we tried to do this experiment by increasing the groundwater level. We see that the model equilibrates. So we reached two conclusions from this. Either this kind of surface hydrologic model is not the right tool to evaluate sea level rise impact on stormwater runoff generation, or stormwater runoff generation is basically a watershed process, and sea level rise increasing the groundwater level through saltwater intrusion, that's more like a local coastal phenomenon. So it's a longer term process, does not necessarily impact stormwater runoff generation at the basin level in the next 30 years. So to keep the area livable, what should we do? Upsize the drainage system. So the runoff is projected to increase up to 100%. So you know that you have to be able to drain that water, twice as much water with the drainage system. So because of the shortage of time, I'll just quickly move on. But before that, I want to tell you that since groundwater level is pretty close to the surface, infiltration-based green technology, and I anticipate it would not be a big part of the solutions. Next slide, please. So just wanted to acknowledge National Science Foundation CRISP grant for this project, and also Florida Public Hurricane Loss Projection Model, which funded the model development. And if you're more interested about this research, you can find more details in the paper that is published last year in Science of the Total Environment. Next slide, please. Thank you.
You can go ahead and read those off. The first one is, can stormwater be moved inland?
Can stormwater be moved inland? Actually, stormwater is an inland overland water. So basically, when rainfall takes place, part of that goes into the ground as infiltration, and part of that would, if it is not humid, let's say, is the air is dry, part of that will go to the air due to evapotranspiration, and the rest of that will be basically, runoff on the ground, inland, basically. So if you don't have enough drainage, which we often see, street gets flooded. And I have seen in 2012, I think 2012 or 13, Dural got flooded by around 5 to 6 feet of water. And it was there probably for several hours until it was drained. So stormwater is indeed an inland water. So in areas not so heavy urbanized yet, such as upstream watershed, how does conversion of natural agricultural land to paved affect runoff? Is it simply more pavement, more runoff? Yes, but not at the same rate as the rainfall increases. This is what we have seen from this research. Would water management of urban green spaces have a significant impact on stormwater runoff? Yes, if you talk about statistical significance, if you study statistics, is the minimum amount of change can be significant statistically, but substantial impact, I doubt in this area. In this area, groundwater level is pretty high. So when it rains, it comes very close to the surface. So in terms of green infrastructure, such as, let's say, rain garden, okay, those would not be very effective. Maybe it will be a very small part of the solution. I think this area would need more of structural and engineering solutions. It's my opinion. There can be more reservoirs. That's also, I consider that a part of the engineering solution. How do we account for and mitigate increased drainage and ET influencing interior wetland with lower groundwater? Okay, so this is an interesting question. So we can, if I understood the question, we can upsize our canals, existing canals. Now, stormwater is expected to increase by 100%. Okay, so does it mean that we are going to increase the canal size by 100%? Not necessarily. We can build more stormwater, what should I say, retention ponds. We have those in Everglades, so we can. In Miami, I lived in Miami for 4 years. I have seen that it has done some unique things, like every neighborhood has a wetland or a pond. So we can increase those, or we can dig them deeper, so that water can drain immediately. Stormwater can drain immediately. Now, interior wetlands with lower groundwater, I'm not so sure whether that is a serious problem, because groundwater level is expected to increase. Even though near the coastline, it can still push water up a little bit in the interior wetlands. what did you mean by the green technology that would not be very effective? I meant green technologies such as green spaces, for example. We want green spaces, but remember, those work by infiltration. That's the main mechanism. Since groundwater level is pretty high in this area, when it rains, it comes to even to the surface. So how much infiltration do you expect out of that? Okay, that's what I meant, such as rain garden. Okay,